In this video, we're going to talk about the rate equation and how you calculate the rate constant using graphs and using data. Now, the rate of reaction is calculated by the change in a property over time, and the three properties are concentration, volume, and mass. And I'm just going to remind you of those 3 units for rate if you have those 3 different variables. So concentration divided by time is the units of moles per decimeter cubed for concentration and seconds for time. Means that it'll be moles per decimeter cubed, seconds minus 1, because raising this up to be the numerator is like timesing it by -1. We then go to the volume over time. The volume over time is centimeters cubed divided by seconds. And so again, this seconds becomes -1, and the rate is centimeters cubed seconds minus 1. We then go over to mass divided by time. This mass divided by time is grams per second, therefore grams seconds minus 1. But we're going to use rate equals concentration over time in 99% of our questions, so we're going to keep that here. And then look at the rate equation and remind you of that. So we have the rate constant, and then we have the reactants here and their concentrations. Remember, we can have 1, 2, 3 reactants. Okay, it doesn't have to be A and B, these are just representations. So here, those concentrations are in square brackets, which is an important point to remember, and then they're raised by the powers that are the orders. We determine the orders through, first of all, graphs. So let's have a look at these rate equations. We're going to consider each one of these types of reactants, whether it be a 0 or a first or a second, and they produce these rate equations if we're considering just A. From there, we can do 3 types of graph, and we can see that these are time concentration graphs. So what we can see here is this negative line going down, just a nice straight line. And then what happens as you go across, you can see it starts to bend, and it starts to almost like be pushed down. And then it gets pushed down really far here, and you can see this line is going down, down, and down. And we see these 3 shapes. Now I describe the shapes in that detail because really you need to recognize these without these labels on them. So I think you should label these graphs sometimes without these axes titles, because they will ask you in multiple choice questions to recognize these without. Anyway, let's go on to the rate concentration graphs. So the concentration is the x-axis here and the rate is the y. And you can see as the concentration of A is going up, the rate is not changing. And that's your 0 order reactant. You then go to this proportional relationship for first. So as A is increased, the rate will increase by the same amount. So if you double A, you double the rate. If you half A, you halve the rate. We then go to this second order graph, and this second order graph means that the rate will change by the square of the change in concentration. So if I double the concentration, you will quadruple the rate. Now, as I said, you need to recognize all of these without the axes. We're now going to look at how to determine the orders through data. So here you have data, different experiments, and the concentration of A, B, and C, and the reactants. So we've got A, B, and C as our reactants here in our equation. You've got to see how the concentration of these reactants change, and how does that affect the rate. So to remind ourselves what happens, 0 order, the rate does not change with concentration. So all of these that we've listed here related to that concentration. First order, the rate increases proportionally with concentration. Second order, the rate increases by the square of the change in concentration. So we just have to look at these numbers and say, well, is it increasing proportionally? Does it change? Is it the square of the change of whatever you made in concentration? So what we do is we look at our first set, and luckily for us, our first set, we've got the same concentration for A, same concentration for C, and we just change the concentration of B. If you look at the concentration of B, it has divided by 3. Now if that's divided by 3 and we go across, we can see that, and we put this into our calculator, and I would pause this and start doing these calculations, and you can see 32.7 divided by 3 is 10.9. So therefore, we've got to divide by 3 in terms of our concentration and a divide by 3 in terms of our rate of reaction. So that's a proportional relationship. And that means we've got a first order reactant. Now, first order reactant means that with the rate equation that we will have, and this is B here, so we'll have to include B and we'll raise it to power 1, which means we just write square brackets B. Let's put that label of first order into our table, and then let's go for the next one. So as you go to the next one, you can see that we're changing the concentration of A, and we're doing that by 3 times. And then if we go across here, you can see that our rate of reaction is staying exactly the same. So it's not changing. So that's why we write 0 order, because the rate does not change with that concentration change. And if it's 0 order, we don't put it in our rate equation. So there will be no A square brackets in our rate equation. Moving on to the next one. If we move on to the next one, we can see times by 4. Remember, we're comparing now B to D. That's because the concentration of A remains the same, the concentration of B remains the same. So we can compare those two. So you don't have to compare A to B, then B to C. You can jump around. Now that means that we've times the concentration of C by 4, times in the concentration by C by 4, but the rate as times by 16. Well, 16 and 4, well, 16 is the square of 4, and therefore the change in rate is the square of the change in concentration. So we think that is second order. Now, if that is the case, we can introduce C into our equation. We've got K, rate equals K, square brackets B times C squared. Let's just go through all of that one more time to make sure you understand. So, times by 3 there, and that is staying the same. So there's our 0 order for our A, and that is your explanation. Now, I'm really putting these explanations on now because this is what gets you mark in the exam. So this is going to get you a couple of marks or a mark in the exam. You say the change in concentration, you then say what happens to the rate, and then you make your justification for what order it is. Well, we know it's 0 order because of that. We then go to the next one. This one, dividing by 3, the other one divides by 3. So again, we make a statement, if this is a question, okay, that B decreases, divides by 3, while rate decreases, divide by 3, which is directly proportional, and therefore we think that is first order. We then go to the last one, which is times by 4, then times by 16. And if that's the case, concentration of C increases by 4 times, while the rate increases by 16 times, increasing by the square of the change in the concentration of C. And notice with all of these, I have put the concentration in square brackets. You can write concentration if you want, but I've just put it in square brackets. That's just as acceptable. And of course, after this, you'll have to justify this and say, A increases by 3 times while rate remains the same, therefore 0 order reactant. B, therefore first order, and C, therefore second order and such. So they're really important to get full marks on possibly an LOR question of 6 marks. So now we've determined the orders and we want to calculate the rate constant K using our experimental data and to do the units. And that will be part of a 6-mark question usually. 1 or 2 marks determining the orders, 3 or 4 marks calculating K, and then 5 or 6 marks can be to do a rate determining step, which is another video. So if we want to calculate K, how do we do it? So all we have to do, because K doesn't change with anything but temperature, it doesn't matter whether you change the concentration, K, the rate constant, will remain the same. So that means we can choose any row to calculate K. So any row at all to calculate K, A, B, C, or D, will come up with the same value of K. And like I said, the rate constant does not change with concentration, it only changes with temperature, and that's really important to remember. So let's get rid of all our data apart from one. So we've got that one piece of data, and let's remind ourselves again, here is our rate equation. So all we have to do is place our rate, and we know our rate is 32.7. Okay, so 32.7, and that 32.7, if I want K, I need to divide that by B and divide by C squared. So if that is the case, B, and I go down here, is 0.3822. So it's 0.3822, that's my concentration of B. We then go to c squared, because we're going to rearrange that. And I think I'll just write that just to make that absolutely clear. So there's your rate, and you've got b, and then c squared, and that will equal your k. All right? And that's all we're doing here. So our rate is 32.7, which we've got from down here. Then we've got a concentration of b, which is down here. And then we want c, which is 0.1956. So there's 0.1956. Let's just elongate that. Okay. And then that is going to equal k. Now, when you put that into a calculator, which you will, that means k is going to equal, and what I would recommend that you do if you're not so good with calculators, let's not forget they're squared, okay? If you're not so good with calculators, is work out this number first, then times it by this number, then use the ANS button, the answer button. So put in 32.7, then divide it by the answer of those calculated together. Now, if that is the case, that will be 2,336, and it'll be 2,336.245. Okay. So normally we do this to however many significant figures they want. So I'm going to do this to 3 significant figures because that is normally what they ask for. So if it's 3 significant figures, that would mean it'll be 2,240 because we round up to there, and that's my 3 significant figures. We're now going to do our units. So our units are going to be based upon here. So I'm going to start over here. So I'm going to go equals. I'm going to put all my units in place. So my rate unit is going to be moles, decimeter cubed, seconds minus 1. Then we put our line again, a bit thicker. And then we've got moles, dm cubed. Okay, that's our first one. That's times moles, dm cubed, and that's squared. So we just applied our squared that is here to our square to here. Okay, we're just taking the unit of 0.1956, putting it there, squaring it just like we've got here, and the unit over there. So we then look at this and we start cancelling out. So I'm going to cancel out that one with that one. All right. Now if I've cancelled out those 2 units, that leaves behind 2 units, and we don't square it. It's a really common mistake, don't square it. Just think of it as 2 times this, okay? So 2 times this. And if that is the case, that means I'm going to do, that will be moles squared, decimeters minus 6. So if we put that down here and say, that would be moles, and that will be moles squared, decimeter minus 6. Okay, we've got nothing up here because we cancelled out apart from our seconds minus 1. So we've got seconds minus 1. And what we need to do is raise that up, and when we raise that up, it's like timesing by minus 1. So you raise it up to be the numerator, it's like timesing by minus 1. And then that leaves us with moles minus 2, decimeters 6, because it's like going from there to there is like timesing by minus 1. Okay, so what we're doing is timesing it by minus 1 to get it up to the top. And when we do that, we get this. And let's not forget our seconds minus 1, which was at the top in the first place. Now, that's a good answer. That's perfectly good. Moles minus 2, decimeter 6, seconds to the minus 1. Okay, that's a really good answer. But what they prefer is for you to put the positive 1 first. So if you're being really, really kind of careful and things like that, you would just swap it around and just put decimeter 6, mole minus 2, seconds minus 1. And that would be the absolute perfect answer. But again, both of them are totally acceptable. Okay, so if, for example, they didn't say to 3 significant figures, you could have 2236.245 moles minus 2, decimeter 6, seconds minus 1. But because we want an absolute perfect answer, we're going to put it to 3 significant figures. Again, only do that if they ask. three significant figures, that's 2240, decimeter 6, moles minus 2, seconds minus 1. And that is how you use data to calculate K and then do the units. We're now going to move on to cover a question where you determine the rate of reaction and K all from a graph. So if we look at this graph, we can see the concentration is here. We can see the time is at the bottom. So it's a concentration time graph. Hopefully we can recognize this shape and think, well, that probably is a first order reactant. To confirm that, never just say it's a first order reactant. If you can, if they're given data, do your half-lives and check that the half-lives are constant. So if we look here, half-lives are constant and they're all 18.5 seconds. Remember as well, half-lives, and we will do a question like this in the exam style question video, but if you look here, you can take a half-life from example 50. So you can start here and then go down to 25 as well. So sometimes they give you a curve when there's not enough data. So be aware of that. If there's not enough data to do this normal half-life where you go from the top, halve it and then halve it again, sometimes you can start from the center. Right, so that constant half-life means that we think that H2O2, because we've got H2O2 going to 2H2O plus H2O, is a first order reactant. So we can do our rate equation. We then rearrange our rate equation, so it equals K. That means we need to know two things. We need to know the rate, and we need to know the concentration of H2O2. If that's the case, let's put that all over to the side, and then start looking at where we get that data. So we get that data, and it's a really important exam tip here, by making a tangent. So the first thing is the rate. We want to know the rate, and we can get it from doing the difference in y over the difference in x, and that's your tangent. Now it happens that y is the concentration, and x is your time. So it's like dividing change in concentration over that change in time, which is your rate. Now the really important thing is here that you've got a times 10 to the minus 3. Always look for this times 10 to the minus 3. Have a good look, turn sideways and look. Times 10 to the minus 3. If that is the case, that means you take whatever number is on here and put times 10 to the minus 3 after it. So if that is the case, we have to line up also that tangent really carefully. And notice that the top of the line is relatively straight, and they'll always make the top of the line relatively straight. That means you can get a very accurate tangent. They can sometimes ask you to do tangents along the line to say what is the rate of reaction at, for example, at 40 or 20, etc. Okay, but most of the time it will be this initial rate of reaction. So like I said, look for that times 10 on the axis, and here is our tangent coming down. The tangent coming down is the initial rate of reaction, and we can take the numbers here and calculate our rate. Now, you might say, where's that 71 come from? Well, the 71 comes from the concentration at 0, okay? Because this is our initial rate of reaction. So at 0, what was the concentration? Which is 71, and we added that times 10 to the minus 3. And then we saw down here 25 seconds, and that's where we get our change in concentration over time, which is 2.84 times 10 to the minus 3 moles per decimeter cubed, okay, seconds minus 1. Now let's keep the rate up there, and now let's look to see of the concentration of H2O2. So we had to have two things. We had to find out the concentration of H2O2 and the rate. Well, it turns out to calculate the rate, we needed the concentration of H2O2, and it's this up here. So you always take it at 0 and that concentration. That gives you a concentration of H2O2, it gives you the rate. And if you remember, K equals rate divided by the concentration of H2O2, which will give you your value of K. So let's get rid of the graph now, and let's do the calculation. So we've got all our numbers. We just need to do our calculation. So we start off with K, and that K is going to be 2.84 times 10 to the minus 3. Okay, and we've got that from here, and that is our rate. So we're doing rate divided by the concentration of H2O2, and the concentration of H2O2 is here, 71 times 10 to the minus 3, and that's our concentration. Let's put it in square brackets. There's your concentration, and there is your rate. Now, at the same time, let's do our units. So our units are going to be moles, dm per dm cubed. That is a rate, so it's going to be seconds minus 1. And then you have this, which is a concentration. That's going to be moles dm per dm cubed. So we can work out now our units on this K. So if you put that into your calculator, okay, that will be a 0.04. Okay, that'll be our final answer. And then if we work out, we're going to cancel out. So we're going to cancel out this. That's our moles per decimetre cube cancelled, which leaves behind our S minus 1. So our unit for this will be S minus 1. So we've used that. So we've taken a graph, and from the graph we found out our initial rate. We've divided it by the concentration of the reactant at 0, which is our initial rate of reaction, and therefore from this rate equation also, which we found out that H2O2 was a first order reactant through our constant half-lives as well, we found out that K was 0.04 seconds minus 1. We're now going to look at calculating K for a first order reaction where we just have one reactant, which is first order, much like we did in the last one with H2O2. Now this is, to this point, or when I recorded this video, I've never actually seen this in an exam, but it is in the specification, and so therefore it could turn up at any point. And what you can do is, if you have a reaction that has a first order reactant only, you can say natural log in your calculator of 2 divided by the half-life. So T half is the half-life, the time it takes for the concentration to halve. So if you have a first order reaction, this T half, this half-life, is constant. So let's have a look at what we did. So we did a tangent calculation before, and we found out it was 0.04 seconds minus 1. Now the reason I might do this is because this is more accurate than taking a tangent. So if you are able to do it, it's a good way of doing it. But like I say, I've never seen it at the point of taking this video or making this video, but you never know. Could turn up. Now, if that's the case, this, like I said, only works with first order as there is a constant half-life, and the units of K would be seconds to the minus 1. Now, let's have a look at how you would do it then. So K equals rate divided by H2O2. We're going to use this H2O2 one that we've done again. Now, if you remember, in this H2O2 equation that we did in the last example, okay, we have found out that the half-life was 18.5 seconds. So all we've done is put the half-life time, 18.5 seconds, in there, and it's worked out as 0.0375 seconds to the minus 1. Now if you compare 0.04 to 0.0375, you can see, well, rounded up, they're both 0.04, but 0.0375 is more accurate. And that's why we might use K equals natural log of 2 T a half. Now the second way you can determine K for a first order reaction, in terms of you just have a first order reactant, is to calculate the K from a gradient. So we've got a graph here, and if you know that graph, it's first order if the rate is directly proportional to the concentration. So if the concentration doubles, the rate doubles. And you can see it from this straight through the origin line here. Now the rate constant is determined by measuring the gradient of this straight line graph. So if we put the gradient on there, we just pick a point in the graph. Because it is a straight line, we can just see what is the difference in rate divided by what is the difference in concentrations. Or simply put, the difference in y divided by the difference in x. And that will equal